Real discovery is a slow, patient process, unfolding layer by layer. And it often starts with something incredibly small. This story begins with a faint speck of light moving across a deep sky image. But that speck turned into one of the most important astronomical discoveries of our time. The third confirmed interstellar comet ever seen by humanity. They named it 3I Atlas. Now, that name might sound simple, but its significance is enormous. This was a visitor from a completely different star system, a traveler carrying the chemical history of a place we can only dream of visiting. Not through theories or distant light, but with a real object right here in our home territory. Instead, it was on a hyperbolic orbit, cutting straight through our solar system. That specific shape is a dead giveaway. It means the object isn't gravitationally tied to our sun. It's just a cosmic tourist passing through on its way back to deep space, never to return. As the observations piled up, it became clear that 3I Atlas was larger than expected, and a bigger comet is a better time capsule. Its interior preserves ancient layers of ice and dust, frozen pages from a book written long before our planet even formed. So, scientists pointed everything they had at it. Giant ground-based telescopes, the Hubble Space Telescope, and, most importantly, the James Webb Space Telescope. Webb's powerful infrared vision gave us a look at the comet's chemical makeup. And what it found made researchers everywhere pause. One compound stood out: carbon dioxide. It had far more co-ice compared to water ice than any comet from our own solar system. This suggested that 3I Atlas formed in a much colder, more carbon-rich environment than the comets we're used to. This finding alone was enough to challenge our models of how planetary systems are built, hinting that the galaxy is far more chemically diverse than we ever imagined. But then, it got even more interesting. Webb detected traces of complex organic molecules. These are the carbon-based compounds that, while not life themselves, are the fundamental building blocks of life as we know it. Let's be very clear here. Finding organic molecules on a comet doesn't mean it's carrying aliens. What it does mean is that the basic chemistry needed for life to begin might be incredibly common throughout the galaxy. If that's true, then the story of life on Earth might not be as unique as we thought. It could be one of many possible outcomes, a natural result of cosmic chemistry playing out in star systems everywhere. Of course, the next big question was, where did it come from? Astronomers measured its motion with incredible precision, then ran the clock backward on its trajectory to trace its origin. This is incredibly difficult. Over millions of years, tiny gravitational nudges from passing stars can alter an object's path, but early analyses pointed to a region just a few dozen light-years away. In cosmic terms, that's practically next door. Sometimes, the biggest surprises in the universe aren't light years away. They're right here, in our own cosmic backyard. That became incredibly clear in early 2025, when the James Webb Space Telescope pointed its powerful eye toward Uranus, a planet most of us only think about when it pops up in a headline. Webb wasn't even looking for anything dramatic. The plan was simple: study the planet's faint rings and grab some atmospheric data. As the first images beamed back to Earth, astronomers spotted a tiny speck of light. This speck moved slowly, consistently, exactly like a small moon should. At first, there was disbelief. How could this be? The Voyager 2 spacecraft flew past Uranus almost 40 years ago, mapping its system with the best technology of the time. How could it have missed a moon? The answer is both simple and humbling. Voyager didn't fail. It missed this moon because it's unbelievably faint and dark, barely reflecting any sunlight. Imagine searching for a black pebble in a vast, dark ocean at night. That's what this was like. The moon was given the temporary name S2025U1. It might sound technical, but it marks the first new moon discovered around Uranus in 2025. At only about 10 kilometers across, it's tiny. But in science, small things can be treasures. Tiny moons hold clues to the history of their entire planetary system. Their orbits reveal ancient gravitational battles, and their composition tells us where they came from. Were they born with Uranus, or were they captured billions of years ago? This discovery really drives home an amazing point. Even in a solar system we've studied for centuries, we're still finding new family members. And Uranus is the perfect example of why modern telescopes, like Webb, are so important. The ice giants, Uranus and Neptune, are some of the most mysterious planets we have, mostly because we've barely visited them. We flew past Uranus just once, in 1986. One quick pass, a few hours of data, and that was it for nearly 4 decades. Webb changed the game. Its infrared detectors scanned the region around Uranus, seeing deeper and clearer than ever before. This new moon stood out because it glowed just slightly warmer than the freezing cold space around it. Now, when I say warm, I don't mean hot. It's the faint infrared signature left by sunlight bouncing off a dark, frozen surface. As astronomers tracked its movement, a fascinating pattern emerged. S2025U1 wasn't orbiting neatly near the planet's equator like the other major moons. It was out in the irregular zone, a region filled with objects captured long after the planet formed. This tells us something huge. Uranus didn't form peacefully. It grew through cosmic violence. Over time, more precise measurements revealed its orbit was slightly inclined and stretched out. That tilted orbit is like a fingerprint. It links the moon to a small family of other irregular moons that share similar paths. The new moon, S2025U1, is one of those fragments, a piece of a world that no longer exists, now just orbiting rubble. There's a strange beauty in that, isn't there? A reminder that not every world survives. Some shatter, some fall, some freeze into silence, becoming evidence for future civilizations to decode. This discovery has also reignited talks about sending a dedicated mission back to Uranus. NASA has already ranked a Uranus orbiter and probe as a top priority for the future. But before you can send a multi-billion-dollar spacecraft across the solar system, you need a good map. Every moon, no matter how small, matters for planning safe orbits and flight paths. Finding a new moon now is much, much better than discovering it by accident during a high-speed approach. What's also incredible is that this tiny moon might be interacting with Uranus's rings. The planet's rings are faint, narrow, and have surprisingly sharp edges. That sharpness doesn't happen on its own. It's often caused by small shepherd moons that use their gravity to keep ring particles in line. Saturn has several of these, and it's likely Uranus does too, but they've been almost impossible to see until now. 2025 U1 might be one of those shepherds, helping to shape the rings from afar. Just imagine for a second what it would be like on this moon's surface. You couldn't really stand because its gravity is so weak. A strong jump could send you drifting into space forever. Above you, Uranus would dominate the sky, a massive blue-green sphere hanging in the darkness. The sun would just be a very bright star, not a disk. The cold would be unimaginable. And yet, this frozen rock tells a story of the early solar system, a story of capture, collision, and quiet survival. Every new object like this adds another piece to the puzzle. We still don't know how many moons Uranus truly has. There could be dozens more, maybe even hundreds of tiny fragments, so dark that we won't find them for decades. But Webb has shown us that if you look hard enough, hidden worlds will appear. The scientific community reacted with this amazing mix of excitement and humility. Discoveries like this are a powerful reminder that even our nearby worlds are still strangers. We can build telescopes that see galaxies at the dawn of time. Yet the space just beyond Saturn holds secrets we haven't even begun to uncover. The outer solar system isn't a quiet, empty place. It's a museum of frozen histories, and moons like S2025 U1 are the artifacts. As we discover more of these irregular moons, a pattern is forming. Many seem to belong to families created by ancient breakup events. Uranus itself was likely knocked completely onto its side by a planet-sized impact. If that's true, the debris from that cosmic catastrophe may still be orbiting today, and this new moon could be part of it. You can see how these small discoveries all connect. A fragment here, a captured object there, each one a clue pointing to a violent and dynamic past. The fact that we can detect these tiny worlds from Earth orbit is a testament to how far astronomy has come. And so, we're left with a simple but profound truth. We are still cataloging our own neighborhood. We are still adding names to the list of worlds orbiting our sun. And every time we do, we remember something important. Exploration isn't a thing of the past. It's happening right now, quietly, patiently, one faint pixel at a time. Thanks for watching. If you enjoyed this journey to the edge of our solar system, don't forget to like and subscribe for more stories from the cosmos. Every once in a while, a discovery comes along that doesn't just answer a question. It cuts right to the heart of one of humanity's oldest mysteries. Are we alone? And in 2025, that question suddenly felt closer than ever to a real scientific conversation. Not speculation, not philosophy, actual data. A rock collected on Mars by the Perseverance rover, a rock now known as Chava Falls, forced scientists to pause and reconsider everything they thought they knew about Mars's ancient past. Let's break it down. For decades, Mars has been the prime suspect in the search for ancient extraterrestrial life. Not current life, though some still wonder, but life from billions of years ago, when the planet was warm, wet, and covered in lakes. That's exactly why Perseverance was sent to Jezero crater. Jezero wasn't picked at random. From orbit, it looks like a dried-up lake bed, complete with ancient river channels and sediment fans. If Mars ever hosted microbial life, that lake would have been one of the best places for it to thrive. In 2024, Perseverance drilled into a reddish, fine-grained sedimentary rock right on the ancient lake floor. The name scientists gave it, Chava Falls, sounds poetic, but the rock itself looked ordinary at first. Then something strange appeared. Dark spots scattered across its surface, surrounded by pale mineral halos. They looked a lot like patterns on Earth created by microbial colonies that burrow into sediments, leaving behind chemical fingerprints. But looking like something isn't proof. It's just a clue, a very tantalizing one that needed careful examination. The rover used every instrument it had. Lasers, X-ray spectrometers, microscopic imagers, organic molecule detectors, and each test pointed to the same conclusion. These features were unusual. Organic molecules were concentrated in the spots, not spread evenly throughout the rock. The halo minerals around each spot could only have formed in the presence of water. Some researchers began whispering the phrase no one wanted to say too loudly, possible biosignatures. But science is strict. A biosignature is only meaningful if you can eliminate every single non-biological explanation first. And that what 2024 and early 2025 were all about, trying to kill the hypothesis that life had anything to do with this rock. Scientists tried everything. They ran chemical reaction models to see if minerals could spontaneously create the same patterns. They compared the detected organics to those found in carbon-rich meteorites to see if they were just contamination. They even scanned the rock's interior with ground-penetrating radar to check for layering that might mimic biological patterns. One by one, the alternative explanations collapsed. The minerals didn't match typical meteorite contamination. The spatial distribution of the organics didn't match random geological processes. The patterns were just too structured, too localized, too intentional looking. In September 2025, NASA made the kind of announcement that turns an entire scientific field upside down. They revealed that all conventional non-biological explanations had been ruled out, not just questioned, ruled out. Now, that doesn't mean the rock contains proof of life, because NASA cannot and will not make that claim without getting the samples back to labs here on Earth. But it means that if you were making a list of hypotheses, the biological one just moved from the bottom of the list right up toward the top. Think of it this way. You're walking through a desert. You see a footprint. At first, you might wonder if it's just wind erosion, maybe an animal track, or a trick of the light. You test every possibility. You poke the sand. You analyze the shape. You study the depth. Eventually, every non-human explanation fails. You still haven't seen the person, but at some point, you have to admit someone might have walked here. That's where we are with Java Falls. The next part of the story is even bigger than the rock itself. Perseverance has already sealed this sample inside a titanium tube where it's waiting for the Mars sample return mission to pick it up. If that mission succeeds, and let's be honest, it's one of the most ambitious engineering tasks we've ever attempted, that rock will arrive on Earth in the early 2030s. Once it does, scientists will throw everything at it. Electron microscopes, molecular scanners, isotopic analyzers, the kind of powerful tests no rover, no matter how advanced, could ever perform on Mars. And here's why that matters so much. If the sample contains fossilized microbial structures, chemical residues of metabolism, or isotopic ratios unique to biological activity, then the implication is enormous. It would mean that life arose twice in one solar system. Not once, twice. That single fact would completely rewrite how we think about the universe. Because if life can emerge independently more than once, right here in our own cosmic neighborhood, then the galaxy is almost certainly full of living worlds. Life wouldn't be a rare fluke. Life would be inevitable wherever the right chemistry and water exist. Even if Java Falls turns out to be a complex geological feature, not biological, it still tells us something profound about early Mars, that its chemistry allowed for complex organic structures to form. Those very structures are the stepping stones to biology. Either way, the planet was once far more Earth-like than the dry, frozen world we see today. There's another angle here. This discovery has strengthened arguments for accelerating human missions to Mars. Robots can investigate, but human eyes, human intuition, and human scientific judgment could dramatically transform how we explore the planet. A geologist standing in Jezero crater might spot formations the rover's cameras would overlook. They could gather hundreds of samples, not dozens. They could drill deeper, explore farther, and react to unexpected findings instantly. But here's the catch. Finding potential evidence of ancient life also reminds us of the danger of contamination. We have to be absolutely certain that when we bring samples home, we don't bring Earth microbes there, and, just as importantly, we don't accidentally introduce Martian chemistry into Earth's ecosystems. The protocols for the Mars sample return are airtight, secure facilities, multiple sterilization barriers, and containment protocols stricter than anything used in high-level medical labs. The stakes are just that high. The emotional impact of this discovery was hard to ignore. Scientists who had been working in planetary geology for decades suddenly found themselves staring at the possibility that they might witness the first real evidence of extraterrestrial life in their lifetime. Students just entering the field realized they might be part of the generation that finally answers the question our ancestors have asked for thousands of years. Are we alone? This is the quiet part of science people rarely talk about. The emotional weight, the responsibility, the sense of wonder mixed with fear, fear of being wrong, fear of getting too excited, fear of misinterpreting what might be the most important rock ever collected in human history. But that fear is also what keeps science honest. The fact that NASA did not declare they found life, even when headlines around the world were screaming it, shows the incredible discipline of the scientific method. You simply don't claim extraordinary conclusions without extraordinary evidence. And that level of certainty can only come from studying these precious samples in the best laboratories we have. For now, Java Falls sits quietly inside a sealed tube, on a distant world, waiting. It has waited for billions of years. It can wait a little longer. And this is what makes 2025 so special. Not because this rock gave us all the answers, but because it brought us to the edge of something truly profound. It reminded us that exploration isn't a story of giant leaps. It's a story of careful, deliberate steps. And sometimes, a single rock can be the stepping stone that leads all of humanity into a new era of cosmic understanding. Thanks for watching. If you found this as fascinating as I do, make sure to subscribe for more stories from the frontiers of science. If you really want to understand how wild and unpredictable our universe is, forget about supernovas or distant galaxies for just a moment. Instead, let's look at one of the most shocking discoveries of this decade, something that felt like science fiction playing out in real time. It's the story of a silent, invisible giant hiding inside a neighboring galaxy, a supermassive black hole, 600,000 times the mass of our Sun, sitting quietly in the Large Magellanic Cloud. It wasn't feeding, it wasn't glowing, it wasn't announcing itself the way black holes usually do, completely dark, completely undetectable, unless you knew exactly where to look. And the only reason we found it at all was because a handful of stars were running away from something they clearly feared. Let's walk through this slowly. The Large Magellanic Cloud, or LMC, is the closest major galaxy to our own Milky Way. If you're in the southern hemisphere, you can actually see it with your naked eye. It looks like a soft, glowing patch of fog in the night sky. For decades, astronomers thought they understood it pretty well. It's a small, irregularly shaped galaxy, full of young stars and gas, caught in a long gravitational dance with the Milky Way. Nothing too exotic, right? Well, that all changed thanks to the Gaia space mission. Gaia is a spacecraft with one single purpose: to measure the exact positions and motions of more than 1 billion stars. It doesn't take those pretty, colorful pictures we're used to seeing. Instead, it takes measurements so unbelievably precise that it can detect a star drifting at the speed of a slow walk from light years away. With that kind of precision, even the tiniest gravitational influences become visible. A few years ago, researchers analyzing the latest Gaia data noticed something very strange. A cluster of stars inside the LMC were moving much, much faster than they should have been. And I don't mean a few percent faster, mean hundreds of kilometers per second faster. They were literally being flung outward, like sparks shooting off an unseen grinder. Now, hypervelocity stars aren't completely unheard of. They usually appear alone, the result of a rare close encounter with a black hole. Imagine one star getting too close, and gravity acts like a slingshot, whipping it out into space at incredible speed. But what Gaia saw in the LMC wasn't one star. It was dozens of them, all moving at different speeds. But when you traced their paths backward in time, all of their journeys intersected at a single, invisible point in space. Imagine looking at a crime scene where every single clue, every footprint, every thread, every marker leads back to one exact spot in the room. That's what astronomers were seeing. A gravitational attacker with no visible signature. So naturally, telescopes all over the world turned to look at that one coordinate. The Hubble Space Telescope, the Chandra X-ray Observatory, huge ground-based observatories in Chile, radio arrays in Australia. And what did they all see? Absolutely nothing. No glowing quasar, no swirling disk of hot gas, no powerful jets, no flickering X-rays, just empty space. But empty space doesn't throw stars around like they're toys. The only thing capable of that kind of power is a massive black hole, and not just a regular stellar black hole, but a supermassive one, hundreds of thousands of times the mass of our sun. And that moment, when the last possible explanation fell away, marked a huge turning point in modern astronomy. It proved something scientists had suspected for years, but could never confirm: that most supermassive black holes in the universe are not active. They are dormant, they sleep, they hide, and they can only be detected by the scars they leave on their surroundings. This is what made the discovery so unsettling and so profound. Every supermassive black hole we had confidently detected before this moment had been loud. They glowed brightly because they were actively feeding. Material falling into them produced so much radiation that it could outshine entire galaxies. But this one wasn't feeding at all. It was a corpse of gravity, sitting silently in the dark. This discovery implies something incredible. The universe is probably full of massive black holes that we have never seen and may never see directly. The one in the LMC was only found because Gaia could measure the tiniest, most subtle deviations in how stars move. Without that technology, this cosmic monster would have remained invisible forever. And here's where the story gets even deeper. The fact that this black hole even exists raises new questions about how black holes and galaxies grow. The LMC is a small galaxy, much smaller than our Milky Way, and yet its central black hole is enormous compared to the size of its host galaxy. That suggests that the LMC might have grown around the black hole, not the other way around. Think about that for a second. The black hole may have existed first a gravitational seed that pulled gas and stars around it over billions of years until a galaxy formed. That's not how we typically picture galaxies forming. And discoveries like this are forcing us to rethink how the early universe really operated. And here's another mind-bending part of the story. The Large Magellanic Cloud is on a collision course with the Milky Way. In a couple of billion years, the two galaxies will merge. That means this silent, sleeping black hole is coming right for us. Very slowly, very gently, but inevitably. When the two galaxies finally merge, the LMC's black hole will sink toward the Milky Way's center and eventually combine with Sagittarius A*, our own supermassive black hole. That merger will release one of the most powerful gravitational wave signals in the history of our galaxy, a ripple in spacetime so big that civilizations thousands of light years away could detect it. Now, don't worry. This won't affect Earth. It will happen long after our species has either transformed or disappeared. Still, the idea that a hidden black hole is slowly drifting toward our galaxy adds an almost poetic dimension to this discovery. A sleeping giant, slowly making its way home. One of the most surprising outcomes of this find was how it completely transformed the way astronomers search for black holes. Instead of just looking for light, because black holes produce no light of their own, scientists now look for motion, for gravitational fingerprints, for disruption. Stars don't just run away unless something is scaring them. Gas doesn't just bend without a powerful force acting on it. Gravity leaves no room for secrecy. So a new era in astronomy has begun. Instead of just searching for bright, active black holes, astronomers are now on the hunt for the dark ones, the ones hiding quietly in galaxies everywhere. The LMC black hole was the first of its kind found this way, and you can be sure it won't be the last. There was also something deeply emotional in how the scientific community reacted to this. It wasn't a flashy, dramatic discovery like a supernova or a new planet. It was subtle, a whisper in the data, a quiet anomaly, and yet its implications were absolutely massive. It showed that even our closest galactic neighbors hold secrets we've completely missed for decades. It reminded us that discovery doesn't always require bigger telescopes. Sometimes it just requires asking better questions. And perhaps the most striking part of it all, this entire discovery started with the slow, gentle motion of a few tiny points of light across the sky. The universe is talking to us all the time, sometimes softly, sometimes violently. The key is simply learning how to listen. Even in the galaxies closest to us, there are giants asleep in the dark, shaping the cosmos without ever revealing themselves. And for the first time, we finally caught one in the act. Thanks for watching. If you found this as fascinating as I did, make sure to like, subscribe, and hit that notification bell so you don't miss our next journey into the cosmos. See you next time. Every time we think we've figured out how the universe began, something new comes along and forces us to rewrite the opening chapters of cosmic history. In early 2025, the James Webb Space Telescope did exactly that. It found a supermassive black hole in a galaxy that existed just 570 million years after the Big Bang, a time when the universe was just a newborn, barely learning how to make stars. The discovery came from a faint, distant object labeled Canucks LRDZ 8.6, one of Webb's deep field targets. At first glance, the image was nothing special, just a small red smudge at the very edge of visibility. Astronomers would typically classify it as an ancient spark, one of the earliest candles lit in the cosmic darkness. But then, the spectral data arrived, and the numbers just didn't make any sense. There was way too much light in wavelengths associated with material falling into a black hole, far too much for such a young galaxy. When researchers calculated the mass needed to produce that signal, the result was staggering. A black hole roughly 10 million times the mass of our Sun, sitting comfortably at the center of a galaxy that shouldn't have had time to grow one. According to all our existing models, this shouldn't have been possible. We thought black holes grew slowly and gradually, through steady feeding or by merging with other black holes over billions of years. But this one was already a monster, only 500 million years after the Big Bang. It's like walking into a nursery and finding a fully grown adult sitting among the infants. So, how did it get there so fast? Let's break it down. The standard theory says that after the very first stars formed and died, their cores collapsed into black holes just a few dozen times the mass of the Sun. These small seeds then grew over hundreds of millions of years as their host galaxies merged and gas pooled into their gravitational wells. But this black hole wasn't a small seed. It was a giant. And a giant needs one of two things: a lot of time or a massive head start. Webb's discovery shattered the idea that time alone could explain it. This leaves us with two main possibilities, and both of them challenge our long-held assumptions about the universe. The first is something scientists call a direct collapse black hole. Instead of forming from a dying star, this kind of black hole is born when an entire massive cloud of primordial gas collapses directly into a black hole, without ever even igniting into stars. No supernova, no messy explosions, just a colossal, inward fall that skips the entire life cycle of normal star formation. This would create a seed that's already thousands, maybe even hundreds of thousands of times the mass of the Sun, large enough to grow into a supermassive, giant astonishingly fast. The second possibility points to a universe far more chaotic and violent than we ever imagined. Maybe early galaxies were constantly crashing into each other. Maybe small black holes were colliding rapidly, combining into larger and larger objects in a cosmic pileup. If the young universe was dense enough, busy enough, and wild enough, then this rapid merger scenario could produce giants early on. But either way you slice it, something is seriously wrong with the timeline we thought we understood. And this is where the discovery gets even stranger. Not only was the black hole enormous, it was actively feeding. Material spiraling toward its event horizon released an incredible amount of light that had traveled for over 13 billion years before reaching Webb's mirror. That light carried information about what the universe was like when it was just a child. By studying the wavelengths Webb detected, astronomers could figure out how fast the black hole was growing, how hot the gas around it was, and how violently matter was being torn apart at the edge of oblivion. If you could somehow stand near that galaxy, you'd see a night sky glowing with radiation from some of the first luminous objects ever created. You would witness black holes and stars forming in ways that no longer happen today. The early universe wasn't peaceful. It wasn't empty. It was a raging storm of creation. There is something else remarkable about this discovery. What it tells us about the era of This was the time when the first stars and galaxies flooded the universe with light, transforming the opaque cosmic fog into the transparent cosmos we see today. Supermassive black holes like this one may have played a major role in that transition. When they feed, they blast out tremendous energy, enough to ionize hydrogen gas across vast distances. This would make them some of the earliest and most powerful contributors to lighting up the universe. This black hole didn't just exist early, it helped shape the cosmos. There's also a philosophical side to all this. For decades, cosmology has been guided by elegant models, simple equations describing a grand cosmic evolution. But nature doesn't care about elegance. It only cares about what actually happens. And 2025 was a stark reminder that the universe is not obligated to follow our expectations. Webb is revealing galaxies with complex spiral structures far earlier than our theories allowed. And now, supermassive black holes emerging before the universe should have had any right to build them. It's becoming clear that the early history of the cosmos wasn't slow or methodical. It was explosive, efficient, and far more organized than we ever anticipated. Scientists are now scrambling to update their simulations. New models are being tested that include rapid gas cooling mechanisms, exotic dark matter interactions, and far more violent episodes of star formation. Some even propose that the very first stars, the mythical population 3 stars, were so enormous and unstable that their collapses created unusually massive black hole seeds right from the start. But here's the most exciting part. This discovery is just the beginning. An entire population of them may be hiding in the red-shifted twilight of the early cosmos. A story that begins not with small stars and small black holes gently growing, but with titans erupting into existence, reshaping everything around them. This is why 2025 changed the field of cosmology forever. The more we discover, the more the universe expands, not just in size, but in its complexity, and in our awareness of just how much we have yet to learn. In a universe overflowing with stars and dust and unimaginable distances, it's easy to forget that sometimes the most extraordinary discoveries are the ones sitting quietly next door. A world now known as UJ251c. The moment you hear that number, it sounds cold and technical, but the reality is far more exciting. This is one of the most promising, potentially habitable planets discovered in years, close enough that future telescopes could study it in breathtaking detail. This discovery could change everything we thought we knew about life in the cosmos. Let's break down why. Red dwarfs are the quiet workhorses of the cosmic landscape. They make up about 70% of all the stars in our galaxy. If life exists elsewhere in the Milky Way, statistically speaking, it almost certainly exists around a red dwarf. And GJ251, a small, steady red dwarf in the constellation Lynx, just became one of the best places to look. GJ251c orbits its star very closely, so close, in fact, that its year lasts only 54 Earth days. That sounds extreme, but red dwarfs are so cool and faint that their habitable zones sit much nearer than ours. If Earth orbited the Sun at that distance, it would be a molten wasteland. But around GJ251, that exact distance places GJ251c right where liquid water could exist on its surface. Not too hot, not too cold, just warm enough for oceans. Now here's where things get even more interesting. Because the planet sits so close to its star, it is almost certainly tidally locked. One side always facing day, one side forever trapped in night. Think of it like standing on a world where the sun never moves from the sky, frozen in one position forever. On the other side, eternal darkness stretches across icy plains. But in between, in the thin twilight band, where day meets night, temperatures might be perfect. Powerful winds would constantly move heat from the hot day side to the frigid night side. If oceans exist, they could circulate warmth naturally, creating a global climate system. In a way, life might even prefer the twilight region more than Earth-like conditions. Permanent sunlight means a constant, stable source of energy. But before we dream too big, let's talk about how scientists actually found this planet. The first clue came from something known as the radial velocity method, essentially watching a star wobble. When astronomers observed GJ251 over hundreds of nights, they saw a small but consistent wobble repeating every 54 days. That wobble could only be explained by a planet roughly 4 times the mass of Earth. That makes GJ251c what's known as a super-Earth. It's bigger than our own world, but still rocky, not a gas giant like Jupiter. If you stood on its surface, gravity would feel heavy, not crushing, but enough to make each step feel deliberate. Its atmosphere, if it exists, could cling tightly to the planet, providing a thick, protective blanket against cosmic radiation. Super-Earths are intriguing because they might be even more stable than Earth-like planets, better at holding on to their oceans, and more resistant to atmospheric loss. Some scientists believe super-Earths might be the most common type of habitable planet in the entire galaxy. Powerful infrared scans helped sharpen the measurements. Observatories began watching for potential transits, the moment when the planet might cross in front of its star from our perspective. If GJ251c transits, the game changes completely. Because when it does, we can analyze the starlight filtering through its atmosphere. Imagine sunlight passing through fog. The chemical composition of that fog changes the color and properties of the light that emerges on the other side. By studying that filtered light, we can detect signatures of oxygen, methane, carbon dioxide, and water vapor. We can even look for chemicals that on Earth are only produced by living organisms. These are called biosignatures. This is precisely why GJ251c is such an incredibly promising target. It's close enough that future telescopes, the next generation after the James Webb, could take direct measurements of its atmosphere. We're talking about the actual chemical fingerprints of processes happening on a surface 18 light-years away. Its proximity makes it a prime candidate for the most detailed atmospheric study ever attempted on an exoplanet. Now, let's talk about red dwarfs for a second. Yes, they're stable, and yes, they're incredibly long-lived, but they also have a dark side. They flare. So, a crucial question is, how active is GJ251? Fortunately, this star is older and much quieter than most. Its flare activity is lower than average, making it far gentler on its planets, even those orbiting at close distances. That single detail dramatically increases the odds that GJ251c could have maintained its atmosphere over billions of years. And if it has an atmosphere, everything changes. With an atmosphere, heat can be distributed between the day and night sides. With an atmosphere, water can remain liquid on the surface. And with an atmosphere, chemistry becomes complex enough to potentially support biology. But here's one more mind-blowing twist. These ambitious missions will use something called a Starship, a massive, flower-shaped satellite positioned thousands of kilometers away from a telescope. Its job is to precisely block the overwhelming light of the star without blocking the faint light reflected by the planet itself. With a starshade, we could take an actual picture of this world, not a blur, not a single pixel, a real picture. We might be able to see its clouds swirling in the atmosphere. We might distinguish the glint of oceans from the texture of continents. We might see its surface colors, or even the faint glow of atmospheric scattering in its perpetual twilight zone. That's the kind of image that would make all of humanity pause and look up at the sky. And yet, among all these incredible scientific details, the part that lingers is something quieter, more profound. This planet is close enough. The Tintheria probe, traveling at a significant fraction of the speed of light, could reach it within a single human lifetime. We're not there technologically, not yet, but the idea no longer feels like distant or abstract science fiction. We've already tested light-sail prototypes in space. We're already designing advanced propulsion systems capable of accelerating tiny spacecraft to unimaginable speeds. One day, a mission could leave Earth and arrive at GJ251c in just a few decades. Imagine being born on Earth and living long enough to see images transmitted from a world orbiting a star 18 light-years away. A world where dusk lasts forever. A world that might host deep oceans beneath a pale red sun. A world that might, just might, contain life. GJ251c isn't just another exoplanet discovery. It's a milestone. It's a signpost pointing us toward the future of exploration. We're getting closer. We're learning where to look. We're learning how to listen for the faint chemical whispers of life from across the stars. And 2025 will be remembered as the year we first realized it was standing right next door, waiting to be seen, waiting to be understood, and maybe one day, waiting to be reached. Thanks for watching. If you found this as fascinating as I did, be sure to follow 4 more journeys into the cosmos. When we think about the early universe, what comes to mind? Probably a chaotic mess. Giant clouds of gas just drifting around, stars popping into existence all over the place, and galaxies. Well, they were probably just awkward, clumpy blobs, still figuring out what shape they wanted to be. For decades, that's exactly what astronomers believed. The idea was that the early cosmos was raw, unstable, and way too young to create the elegant, swirling spirals we see in galaxies like our own Milky Way. And then 2025 arrived, bringing a discovery that quietly shattered that entire picture. A deep observation from the James Webb Space Telescope revealed a galaxy nicknamed Alandandanda, fully structured, mature spiral galaxy that existed just 1.5 billion years after the Big Bang. Now, to put that into perspective, if the entire history of the universe were squeezed into a single year, this galaxy would have formed before the end of February. It was just too early, too organized, too beautiful for a universe that was still supposed to be in its awkward teenage phase. But there it was. A spiral, a real one, with curved arms, a rotating disk, and a stable core. Everything our theories said shouldn't exist that early. So let's break this down, because this discovery is so much bigger than just a pretty picture. Spiral galaxies don't just pop into existence. They need time, hundreds of millions of years, to settle down, for their gas to form a thin disk, and for those beautiful arms to take shape. They need calm, predictable conditions. The early universe was supposed to be the opposite of calm. It was a violent place, full of mergers and collisions that would have ripped any delicate structure to shreds. But Alandanda was different. Its perfect spiral shape didn't just challenge our models. It completely overturned the timeline of galaxy evolution. The first clue came from Webb's powerful infrared vision. Light from this distant galaxy, stretched out by the expansion of the universe, revealed a subtle but unmistakable pattern, arms curving around a bright center. When astronomers ran simulations to figure out what kind of motion could create that shape, they found something stunning. This galaxy was spinning with the smooth, disciplined rotation you'd expect from a mature spiral billions of years older. That meant one of two things had to be true. Either our entire understanding of how galaxies form was fundamentally flawed, or this galaxy somehow went through an incredibly fast, efficient evolution we never thought was possible. And this is where it gets even more fascinating. When researchers analyzed the galaxy's chemical makeup, they didn't find the simple, basic elements they expected from the early universe. Instead, they found metals heavier elements that are forged inside stars and scattered when they die. This meant Alandanda had already gone through multiple cycles of star birth and death. Not just one generation of stars, but several. A galaxy that young simply shouldn't have had enough time for all that. So, how did it happen? One leading idea is that the halos of dark matter, the invisible scaffolding of the cosmos, clumped together much faster than our models predicted. If these dark matter pools formed earlier and were denser, their gravity could have pulled gas into a rotating disk much sooner. That could explain the galaxy's organized spin. Another possibility is that the streams of gas feeding the galaxy were incredibly efficient. Imagine gas flowing in like a gentle river instead of crashing waves. Smooth inflows create stable disks. Violent mergers destroy them. If Alandanda grew up in a calm cosmic neighborhood, its early maturity starts to make a lot more sense. But the most radical idea is this. What if spirals aren't the latecomers we thought they were? What if they were among the very first stable structures the universe learned how to build? If that's true, it changes everything. It shifts our view of the early cosmos from one dominated by violent crashes to one shaped by elegant, rapid self-organization. Imagine the universe not as a turbulent ocean in its youth, but as a place where gravity could carve out order much earlier than we ever dreamed. Another piece of the puzzle came from measuring the galaxy's star formation rate. Normally, young galaxies burn through their gas like wildfire, creating stars at an explosive, chaotic pace. But Alandanda wasn't doing that. Its star formation was high, yes, but it was controlled, regulated. That's another sign of maturity, a galaxy that knows how to pace itself. It's like meeting a teenager who has the calm wisdom of a much older adult. This single discovery has sent ripples across the entire field of cosmology. If one spiral galaxy existed that early, there must be more. And in fact, Webb has already hinted at other faint, spiral-like shapes in its deep field images. This suggests that early spirals might not have been rare at all. We just couldn't see them until now. It also forces us to rethink how galaxies evolve. The old story was that galaxies started as messy blobs, smashed into each other for a few billion years, and then eventually settled down. But if spirals formed early, then maybe mergers aren't the main characters in this story. Maybe internal processes like rotation, gas cooling, and dark matter patterns play a much bigger role from the very beginning. One of the most surprising details from the 2025 observation was that Alandanda's rotation speed was similar to modern spirals like our own Milky Way. That means its mass was already perfectly balanced between its disk, its central bulge, and its invisible dark matter halo. Again, this happened far earlier than anyone expected. If you could magically transport yourself inside this galaxy, the night sky would be dazzling. It would be filled with brilliant, massive blue stars, burning intensely and dying young, enriching the galaxy with new elements. And through that cosmic haze, you'd see the spiral arms already stretching outwards, like the petals of a flower just beginning to open. It's a breathtaking image, but there's a deeper message here. Galaxies aren't just passive objects shaped by cosmic accidents. They are dynamic systems capable of organizing themselves with astonishing speed. The early universe, far from being a chaotic wasteland, may have been a place where structure and beauty emerged far more elegantly than we ever believed. This discovery also strengthens a powerful new idea that dark matter halos don't just contain galaxies, they actively shape them. If the halo forms early and smoothly, the ordinary matter inside might just follow its gravitational blueprint, forming disks and spirals with incredible speed. There's a philosophical angle to this, too. We tend to imagine the universe's first billion years as crude and unfinished because that's how our human world works. Babies grow slowly, trees mature slowly, but the universe doesn't follow our timeline. It organizes itself with an efficiency that defies our sense of time. Alandananda is proof of that. It's a reminder that the early cosmos wasn't a blank slate, but a workshop that was already building masterpieces. And maybe the most extraordinary thing about it is that this galaxy wasn't a giant. It wasn't some rare, colossal monster. It was just a normal-sized spiral galaxy, forming early, quietly, without any drama. And its very normalcy is what makes it so revolutionary. It suggests that this might have been the standard way for galaxies to grow, much earlier than we thought. By the end of 2025, astronomers were already busy rewriting textbooks and redesigning their simulations. The entire timeline of cosmic history shifted, all because one faint spiral, billions of light years away, dared to exist before our theories said it could. We think we know the outer solar system. Take Saturn. It feels familiar, right? Those iconic rings, the soft golden glow, moons we learned about as kids like Titan and Enceladus. Saturn feels mapped out, almost comforting. But in mid-2025, that illusion was completely shattered. Astronomers announced something so overwhelming it forced scientists to rethink everything they knew about this gas giant. Saturn didn't just gain a moon or two. It didn't even gain a dozen. It gained 128 new moons, all at once. Overnight, Saturn reclaimed its title as the King of Moons, boasting a staggering 274 known satellites. That's far more than Jupiter, far more than any other planet in our solar system. Now, these aren't massive worlds like Titan, they're tiny. Some are only a kilometer across, others maybe 10, but they are moons, each a real orbiting body with its own path, its own history. What makes this discovery so incredible isn't just the sheer number, it's what these moons represent. Because Saturn's newest satellites aren't regular moons, the kind that form peacefully from a disk of gas and dust. No, these are irregular moons, and irregular moons tell violent stories. Irregular moons don't orbit neatly along the planet's equator. They aren't round, and they don't travel in tidy circles. Instead, their orbits are tilted, elongated, and chaotic. Some even orbit backward, in strange retrograde loops that defy our intuition. This is the unmistakable signature of captured objects. Picture the early solar system. It was pure chaos. Asteroids slammed into planets, comets screamed past at incredible speeds, and massive debris clouds stretched for millions of kilometers. In the middle of all that, Saturn acted like a giant gravitational net, passing objects. Saturn's immense gravity would slow them down just enough to trap them in a permanent orbit. Those captured bodies became irregular moons. But capturing an object is rarely a clean process. Sometimes they collided with existing satellites. Sometimes they shattered upon capture. Sometimes dozens of fragments would scatter into their own independent orbits, each one becoming a new moon. And that's probably what we're seeing with these 128 new discoveries. They aren't 128 individual stories, but rather families. When astronomers plotted the new moons on orbital graphs, clear patterns emerged, clusters formed. Some moons shared nearly identical inclinations. Others shared similar distances from Saturn. Some even traced matching retrograde loops. These families are the fingerprints of destruction, evidence of a single object being smashed into many pieces. Some of these collisions may have happened hundreds of millions of years ago. Some might even be older than Saturn's rings themselves. And that's where things get even more interesting. For decades, scientists have debated the age of Saturn's rings. Are they young, maybe only 100 million years old? Or are they ancient, formed alongside Saturn itself? One leading theory suggests that rings might form when a small moon strays too close to the planet and gets torn apart by its powerful tidal forces. Such a moon would shatter into countless icy fragments that spread out to form a ring. Now, imagine this. If Saturn has dozens upon dozens of small, irregular moons wandering in unstable orbits, the chances of occasional close passes or collisions increase dramatically. This enormous population of fragile, irregular bodies might just be the missing link in understanding Saturn's rings. Maybe the rings formed from shattered moons. Maybe they formed this way multiple times over the planet's history. Perhaps they are constantly being replenished, fed by occasional moon-to-moon collisions that grind small bodies into dust. The discovery of 128 new moons makes the entire system look less like a quiet, orderly set of rings, and more like a crowded, ongoing cosmic debris field. But that's just one side of the story. There's also a practical challenge: naming them. The convention for Saturn's moons is to pull from Greek and Roman mythology, titans, giants, and children of the gods. But we have a problem. Saturn doesn't have a handful of moons anymore. It has nearly 300. We're literally running out of mythological figures. Future naming schemes may need to expand into other mythologies: Norse, Celtic, Hindu, Mesopotamian, or we might just have to stick with provisional designations. You can only name so many cosmic rocks after ancient gods before the list gets pretty thin. So how were these moons even discovered? The breakthrough didn't come from a single telescope, but from a combination of deep exposure surveys using some of the world's largest observatories. The technique was simple in concept, but incredibly difficult in practice. Track faint, moving objects across dozens of hours of stacked images. Most of these moons reflect almost no sunlight. Many are as dark as charcoal. They're tiny, distant, and completely hidden in Saturn's glare. Only when astronomers painstakingly stitched together hundreds of exposures taken over long periods did the dots begin to move. A faint pixel here, a faint pixel there, then a curve, then an orbit, then finally a moon. It's a powerful reminder that the outer solar system isn't empty. It's teeming with debris we've barely begun to detect. As our telescopes get more powerful, the number of known moons will likely keep rising. Jupiter, Uranus, Neptune, they almost certainly have hundreds of tiny moons we haven't found yet. But Saturn's situation is unique. Its gravitational environment is ideal for capturing objects. Jupiter's enormous gravity tends to eject more bodies than it captures, flinging them out of the system. Saturn, with its gentler pull and huge sphere of influence, captures and keeps. This is why Saturn now holds the crown for the most moons in the solar system. Think about this from another angle. Every moon, no matter how small, carries a record of its past. Its shape, its orbit, its composition all are clues to ancient collisions, ancient migrations, and ancient captures. Some of Saturn's new moons probably came from the distant Kuiper belt. Some may have been rogue objects wandering between the planets. Others could be fragments of larger moons that are long gone. Some may hold primordial material older than the Earth itself. And yet they're so small that a person could walk across one in about half an hour. When future missions travel to Saturn, these tiny moons become incredibly tempting targets. Imagine a lander touching down on a 2-kilometer-wide worldlet, where gravity is so weak you could push yourself into space with a gentle jump. Imagine collecting samples from a piece of rock that has never been warmed, never been altered, never been part of a planeta-preserved relic from before our solar system had any structure. These little moons might seem mundane in size, but their scientific value is immense. And here is something people often overlook. Saturn's irregular moons give us a window into how planets form in general. Giant planets don't just gather satellites, they gather histories. Every captured object is a survivor from a different environment. Every collision is a chapter in a chaotic past. Every fragment is a clue to how the early solar system shaped itself. Saturn isn't just a planet, it's an archive. And in 2025, someone opened a new drawer in that archive and found 128 new stories sitting quietly in the dark. When you look at Saturn through a telescope, what you see is only the beginning. The rings dazzle the eye, and Titan steals your attention. But orbiting far beyond them, faint and silent, are hundreds of tiny worlds following tilted, looping, retrograde paths forged by billions of years of gravity and chance. The outer solar system is a museum of ancient motion, and Saturn might just be its most dramatic gallery. The discovery of these moons doesn't close a chapter. It blows a new one wide open. Now, we have to ask new questions. Why are some moon families so tightly grouped? How often do collisions happen? How many moons has Saturn destroyed over its lifetime? And how many new ones will we find next year? Each answer leads to another question, and each question leads us deeper into the story of how a world like Saturn becomes what it is. In 2025, Saturn reminded us of something important. The closer we look, the more complex and beautiful the universe becomes. And that complexity is a gift and invitation to keep exploring. When we think about exploring our solar system, we usually picture the big mysteries, icy moons, distant planets, or comets from beyond Neptune. But what if the most revealing clues were hiding in plain sight, in objects so small we barely knew they existed? In 2025, NASA's Lucy spacecraft proved this to be true during its flyby of a tiny asteroid named Donalja-Hansen. This wasn't some flashy, dramatic event. It was quiet, precise, and deeply scientific. And that's exactly why it was so important. The Trojan asteroids, which share Jupiter's orbit around the Sun, are some of the oldest, most untouched relics of the early solar system. They're leftovers from the time when planets were just beginning to form. They are cosmic time capsules. Lucy's mission, while simple in concept, is incredibly ambitious. Visit as many of these Trojans as possible, up close, and figure out what they're made of. Donalja-Hansen was never meant to be the star of the show. It wasn't even a main target. It was just a warm-up, a rehearsal on the way to Jupiter's orbit. It was a chance to test the instruments, calibrate the cameras, and make sure everything worked perfectly for a high-speed encounter. But as often happens in science, the warm-up turned into a major discovery. But the most fascinating details weren't the craters. They were the subtle patterns on the surface, grooves, ridges, and slight changes in brightness. These features hinted at something about its internal structure. Lucy's data suggested that Donalja-Hansen might be what scientists call a rubble pile, a loose collection of rocks held together only by their weak gravity, not a solid piece of stone. This kind of structure is incredible because it means the asteroid survived countless impacts, not by being strong, but by being squishy. Imagine punching a pile of sand. The sand doesn't crack, it just absorbs the force. Rubble pile asteroids do the same thing. which explains how these ancient, fragile objects can survive for billions of years. If Donald Johansen is a rubble pile, that also means it's incredibly porous, maybe up to 50% empty space. These bodies aren't solid mountains. They're more like cosmic coral reefs, full of voids and cavities created by billions of tiny rocks packed loosely together. Now, think about what this means for planetary defense. If a rubble pile asteroid were ever on a collision course with Earth, simply hitting it with a projectile might not work as we'd hope. Instead of shattering into harmless pieces, the fragments might just drift apart and then slowly pull themselves back together under their own gravity. That's why studying these structures is so critical. You can't defend our planet from something you don't fully understand. But the story gets even better. Lucy's spectrometers analyzed the asteroid's surface, revealing a mix of silicates and carbon-rich materials. These are the signature ingredients of the earliest bodies in our solar system, preserving chemical clues about the environment where the asteroid originally formed. And because Donald Johansen is part of the Trojan population, it gives us a window into the chaotic migration of the giant planets billions of years ago. There's a theory called the Nice model, which suggests that the giant planets Jupiter, Saturn, Uranus, and Neptune didn't form in their current orbits. Instead, they moved around dramatically in the early solar system, scattering material everywhere. Some rocks were flung out to the Kuiper belt, others were thrown inward toward the Sun, and some got trapped in stable points in Jupiter's orbit. These trapped remnants became the Trojan asteroids. If this theory is correct, then Donald Johansen might have started its life nowhere near Jupiter, maybe even in the cold outer edges of the solar system, before being captured into its current orbit. That makes it priceless. It carries the chemical fingerprint of a region of space we might never otherwise be able to study. Lucy's data strengthens the idea that the Trojans are an incredibly diverse group, each with its own unique origin story. The early solar system wasn't a neat, organized place. It was a chaotic blender of materials from all over, and there were more surprises. Some parts of Donald Johansen's surface appeared unusually smooth. That's very strange for a rubble pile. Smooth terrain usually requires some kind of geological process to erase roughness, like flowing material or settling dust. On an object this small, with almost no gravity, traditional geology just doesn't work. It can't have volcanoes or tectonic plates. So, what's going on? Scientists think that fine dust, created by countless micrometeorite impacts over billions of years, slowly migrates across the surface and settles into low-lying areas, gradually smoothing them over time. It's a silent, incredibly slow geological process happening on a body with almost no gravity. Another fascinating detail: one of the asteroid's two lobes appears to be more heavily cratered than the other. This suggests that the two lobes likely formed in different environments before they merged. They have separate histories literally written on their surfaces. It's a humbling thought. A tiny rock, drifting quietly through space for billions of years, suddenly became a messenger, a witness, and a storyteller. And in 2025, for just a few minutes, humanity flew right beside it and listened to what it had to say. For years, astronomers knew something was off about Betelgeuse, the giant red star on Orion's shoulder, one of the most famous stars in the sky, was acting weird. It flickered, it pulsed, and in 2019, it dimmed so dramatically that everyone started talking. Scientists looked closer and closer, but one question remained. Why does Betelgeuse behave this way? Well, in early 2025, we finally got an answer, and it changed everything. Using the incredible power of the James Webb Space Telescope and the Gemini Observatory, astronomers confirmed that Betelgeuse isn't alone. It has a companion star, a long-hidden partner gravitationally locked in a cosmic dance. They've nicknamed it Beetle Buddy. This single discovery completely rewrites decades of what we thought we knew. Let's back up. Betelgeuse is a monster. It started as a massive blue star, maybe 20 times the mass of our sun. Over millions of years, it burned through its fuel, swelled up, and became the red supergiant we see today. It's so big, if you dropped it into our solar system, it would swallow Mercury, Venus, Earth, and maybe even Mars. A star this huge is naturally unstable. It pulsates, it sheds its outer layers, and it blasts out waves of gas like a boiling pot. But a companion star changes the whole story. Suddenly, Betelgeuse isn't an isolated giant having a midlife crisis. It's part of a pair, and this relationship has shaped its behavior for centuries. This Beetle Buddy is a hot, bright, blue-white star. It's still massive, about 10 to 15 times the mass of the Sun, but next to Betelgeuse's overwhelming glare, it was completely invisible. For decades, we simply couldn't see it. This is where the James Webb Space Telescope worked its magic. Using an instrument called a coronagraph, astronomers basically created a tiny artificial eclipse. Imagine holding your hand up to block the sun's glare so you can see something next to it. That's what Webb did. It blocked Betelgeuse's blinding light, and out from the shadows emerged its faint blue companion. This tugging distorts the supergiant's shape, causing parts of its surface to swell up or collapse, triggering those large-scale pulsations we've observed. The star's surface literally ripples and shifts, all because of its dance partner. This new model also perfectly explains the great dimming of 2019. We know Betelgeuse ejected a massive cloud of dust that temporarily blocked our view. But why then? This extra stress could have triggered Betelgeuse to shed material more violently than usual, creating that giant dust cloud. The companion didn't cause the dimming directly, but it absolutely set the stage. Then there's the matter of its spin. Betelgeuse rotates surprisingly fast for a star of its size. Normally, when a star expands into a supergiant, its rotation slows down, like a figure skater extending their arms. But Betelgeuse seems to have kept more of its spin. A companion star explains this. In binary systems, stars can transfer momentum to each other. Beetlebuddy might have been stirring Betelgeuse's outer layers for millennia, spinning them up. This extra rotation could be why higher resolution images show a turbulent, boiling surface, not a smooth ball of gas. This discovery is huge for another reason. Betelgeuse is going to explode. Not tomorrow, probably, but someday in the next 100,000 years, it will go supernova. When it does, it will be an absolutely spectacular sight, bright enough to outshine the full moon and be visible during the day. The presence of a companion star will dramatically change this final act. In some cases, a companion can strip away the supergiant's outer hydrogen layers before it explodes. This would change the type of supernova we see, possibly turning it into a much rarer subtype. It could also make the explosion lopsided, sending more energy in one direction than another. Billions of years from now, future astronomers studying the wreckage of Betelgeuse might see the distinct fingerprint of a binary interaction, a final message from Beetlebuddy. And what about the strange, uneven dust shells we've seen around Betelgeuse? Infrared images have revealed arcs and loops of material stretching away from the star, like cosmic smoke rings. They were too organized to be random, but too messy to fit any simple model. There's one more consequence that's easy to miss but has a massive impact. We have to rewrite the textbooks. For decades, Betelgeuse was the poster child for how single, massive stars live and die. But that model was wrong. Everything from its mass loss rate to its pulsation has to be re-examined through the lens of a binary system. What's really fascinating is that binary systems are not rare at all. In fact, most massive stars have companions. Our Sun is actually the odd one out. So maybe Betelgeuse, with its hidden partner, is more normal than we ever thought. It was our assumption that was unusual. For thousands of years, humans have looked up at that single red point of light. We used it to navigate, wove it into our myths, and watched its flickering, wondering if it was about to explode. But it was never alone. It had a silent partner hiding in plain sight, a companion whose existence we only just uncovered because we finally built tools sharp enough to see it. Betelgeuse wasn't just being dramatic, it was living the complicated, messy life of a binary star. But don't just see a single point of light. Imagine two giants, locked in a slow gravitational waltz that has lasted for ages. A dance whose effects ripple across the cosmos. In 2025, we finally learned the truth. Betelgeuse isn't just one star on the edge of collapse. It's a relationship, a partnership, a story of two ancient suns sharing the final chapters of their incredible lives. Here's what made late 2025 feel so different from any other year in cosmology. For a while, things had been quiet. Astronomers weren't really expecting any big surprises. The major questions about the universe felt, well, settled. Our standard model, the rule book that explains how galaxies move, how everything is distributed, and how the universe is expanding, seemed solid, stable, almost unshakable. And then a single measurement came along and broke the silence. It was a result that looked simple on the surface, but was so disruptive that its implications sent ripples through every corner of cosmology. It turns out our solar system is moving through the universe far faster than we ever thought. I don't mean a little faster, not even double. We're talking 3 times faster. For decades, we believed our speed, measured against the cosmic microwave background, that faint afterglow of the Big Bang, was about 370 kilometers per second. But a new radio galaxy survey in 2025, which combined data from the LOFR telescope and other global arrays, came back with a number closer to 1,000 kilometers per second. That's around 620 miles every single second. Almost 3% of the speed of light. And here's the really astonishing part. The measurement wasn't a mistake. It wasn't a calibration error, or a misinterpretation, or some statistical fluke. It held up across different instruments, different observational methods, and different maps of the sky that left only one possible conclusion. Something huge is pulling us, something we cannot see, something that isn't included in any of our current cosmological models. To understand how we found this out, we need to talk about the Doppler effect. Not the version you hear with ambulance sirens, but the cosmic one. When light travels from a distant galaxy, its wavelength changes depending on our motion relative to it. If we're moving toward that galaxy, its light shifts just a tiny bit bluer. If we're moving away, it shifts red. The change is incredibly small, so you need extremely sensitive radio telescopes. You need to look at thousands of galaxies spread evenly across the sky, and you need very precise statistical tools to analyze the data. This is the kind of work that only became possible in the last few years, thanks to new wide-field radio arrays and massive improvements in computing power. When astronomers charted all these tiny shifts in every direction, they expected to see a smooth, predictable pattern, what's known as a dipole, that represented our motion. That's what standard cosmology predicted. Instead, they found a dipole that was 3 times stronger than it should have been. It was like nature was shouting a message we never expected to hear. You are moving much, much faster, and you have no idea why. The first thought, naturally, was to look at dark matter. Maybe it's distributed differently than we assumed. Maybe there's a massive, unseen structure out there, giant supercluster of galaxies, exerting a powerful gravitational pull. But when they ran the calculations, something troubling emerged. To pull our entire Milky Way galaxy up to a speed of 1,000 kilometers per second, this structure would have to be far larger and more massive than any known cluster in our cosmic neighborhood. Could it be an enormous supercluster beyond the edge of our visible universe? It's possible. But that would require a scale of structure that is completely unlike anything our current theories predict. Then another possibility started to take shape, one that was even more profound. Perhaps our standard model of cosmology itself, the Lambda CDM model, is missing something fundamental. Maybe dark energy isn't perfectly uniform across the universe. Maybe the large-scale flows of matter are more chaotic than we thought. Maybe the expansion of the universe isn't as smooth and orderly as our textbooks have told us for decades. This wasn't just a small crack in the theory. It was a direct challenge to one of the most fundamental ideas in cosmology, the principle of cosmic isotropy. That's the idea that, on the largest scales, the universe looks the same in all directions. If that principle breaks down, then everything we calculate, the expansion rate, how galaxies form, the age of the cosmos, how matter is distributed, all of it has to be revisited. And so, in late 2025, many cosmologists found themselves asking a question that would have been unthinkable just a decade ago. Is the universe actually lopsided? Now, to be clear, this doesn't mean the universe is physically stretched out of shape like a balloon. It means the distribution of matter and energy might not be as even as we always assumed. There could be enormous cosmic voids that are effectively pushing us away, or massive clusters pulling us in. Dark energy might not be a constant, but could vary from one place to another. Or maybe there's a deeper physical rule at play, something we have undiscovered yet, that influences motion on scales far larger than individual galaxies. The most sobering part of this discovery wasn't just the shocking new number itself. It was the simplicity of how it was observed. Astronomers weren't studying exotic particles or looking for rare one-off events. They were measuring something we've had for a long time, the oldest, most universal reference frame available to us, the cosmic microwave background. If you want to know how fast your really moving through space, that's your ultimate benchmark. Everything else in the universe drifts, evolves, and moves. But that background radiation is the closest thing we have to a true cosmic zero point. So, when the background tells you you're moving faster than you thought, there's no easy way to argue with it. Let's just pause for a moment and appreciate the sheer awe in that idea. Right now, as you're sitting there watching this, you are hurtling through the universe. The Earth is spinning on its axis, it's orbiting the Sun is orbiting the center of the Milky Way, and the entire Milky Way galaxy itself is flying through cosmic space at speeds that are almost impossible to imagine. We are all living inside a cosmic river. And we just learned that the current is far stronger and faster than we ever realized. This is where the really big philosophical questions start to kick in. But here's a quiet little twist that scientists are now discussing. Maybe the universe is more dynamic and less uniform than we believed, not because our theories were wrong, but because we simply didn't have the tools to see this deeper structure until now. 2025 finally gave us those tools. We have radio arrays that can map the sky in unprecedented detail. We have computational models that can simulate cosmic flows on scales that were once impossible. We have better analysis techniques for the cosmic microwave background and new galaxy catalogs that span billions of light years. The universe didn't suddenly change. We just finally learned how to listen to it better. So, what happens next? Well, new surveys will be launched to refine this measurement. Cosmological models will be rewritten from the ground up. Some old ideas will be thrown out, and others will evolve. New theories will emerge to try and explain what's going on. You'll probably be hearing about this discovery again and again in the coming years, because its implications touch everything: how galaxies form, how matter clusters together, how fast the universe is expanding, how old it really is. But maybe the most captivating part of this whole story is this: you are not sitting still in a calm, quiet universe. You are part of a vast, fast-moving structure, a cosmic streak of galaxies, gas, dark matter, and radiation, all rushing through space at 1,000 kilometers every single second. We often think of ourselves as small and insignificant in the grand scheme of things. But a motion like this, a velocity this immense, it reveals just how deeply we are connected to the universe's largest structures. We aren't just passive observers. We are active participants in a cosmic motion that began billions of years before the Earth even existed. And in 2025, for the very first time, we finally measured it correctly. Here's something almost no one expected to happen in 2025. On August 2nd, astronomers scanning the sky with the Pan-STARRS telescope in Hawaii noticed a small, faint object. It was following Earth in a strange, synchronized way. At first, it looked like just another near-Earth asteroid, another rock passing by on its long journey around the sun. But after a few nights of tracking, something didn't add up. The object wasn't passing us. It wasn't moving away. It was staying with us. It seemed as if it had been quietly orbiting alongside Earth for decades without anyone noticing. They named it 2025 PN7. And within weeks, it became clear this wasn't just another asteroid. It was a quasi-satellite, a type of cosmic companion that moves around the sun but appears to hover near Earth for years. Think of it like a runner on a track, pacing right alongside you. You're not tied together, but because your orbits around the track match perfectly, you move in sync. What makes 2025 PN7 so special isn't just that it's a quasi-satellite. We've seen a few of those before. What makes this one extraordinary is its stability. This object has been shadowing Earth for at least 60 years, possibly much longer, and we never even noticed. The reason is simple. It's small, about 200 meters across, roughly the size of a large football stadium. It's too dim to stand out, too close to the sun's glare for most of the year, and its motion is too subtle to distinguish from the background of other objects. But once astronomers locked onto it, things got interesting. A quasi-satellite isn't a moon. Our moon is bound to Earth's gravity. If Earth vanished, the moon would drift off on a new path. But 2025 PN7 isn't gravitationally bound to us. It's orbiting the sun, not Earth. It just happens to orbit the sun in almost perfect synchronization with our planet. Every year, as Earth makes its 940 million kilometer journey around the Sun. 2025 PN7 completes almost the exact same loop. It drifts slightly ahead, then slightly behind, weaving a delicate pattern in the sky like a leaf circling a slow-moving riverboat. It's a cosmic coincidence, but a remarkably stable one. For astronomers, this kind of orbit is a gift. It means the object is close enough to study year after year without having to rush and catch it during a brief flyby. And that makes 2025 PN7 a prime candidate for something nobody expected: future asteroid resource missions. Here's why. Most near-Earth asteroids zip past us quickly. If you want to send a spacecraft, you get one chance every few years, often requiring enormous energy just to match its speed. But a quasi-satellite, it's always around, always accessible, always returning to the same gravitational dance. If humanity ever starts mining asteroids for metals, water, or fuel, we'll need stable targets. 2025 PN7 fits that description better than almost any asteroid discovered so far. But before we talk about resource extraction, we have to talk about the science. And there are some big questions. The first mystery: what is it made of? Spectroscopic analysis is still ongoing, but early observations show it reflects light like a typical stony asteroid, the kind rich in silicates and metal. Another possibility is that it's a carbonaceous asteroid, dark and ancient, containing water-bearing minerals and organic compounds. If it's carbonaceous, 2025 PN7 might hold materials older than the Earth itself. It could be a preserved fragment from the very beginning of our solar system. The second mystery is how it got into this orbit in the first place. Quasi-satellites can form through gravitational nudges from planets, collisions, or chaotic orbital evolution over millions of years. But long-term stability is rare. Most quasi-satellites only stay in their synchronized orbits for a few decades, maybe a century, before drifting away. Not only has 2025 PN7 been with us for decades, simulations show it may remain near Earth for another 150 to 200 years before it slowly peels off into deep space. That makes it a temporary companion, a short-lived second shadow for our planet. Not a moon, but something quieter. A visitor that arrived unannounced, stayed longer than expected, and will one day drift away without ceremony. The third mystery: could it pose a danger? Fortunately, early trajectory models show no threat. It never comes close enough to Earth to risk an impact. Its orbit lies safely within a gravitational cushion where Earth's pull subtly stabilizes it without drawing it inward. There's something profoundly calming about that. A cosmic rock has been circling us for half a century, and only now do we realize it's been harmlessly pacing alongside us, like a quiet traveler who prefers to stay just within view. But here's where things get even more exciting. NASA engineers pointed out something intriguing. 2025 PN7 is at the perfect size and distance for a test mission. A small spacecraft could be designed to land on it, sample its surface, drill into it, or even practice anchoring to a low-gravity object. Because make no mistake, landing on an asteroid is incredibly difficult. Their gravity is so weak you can bounce off and fly away with the smallest mistake. Their surfaces are loose, unpredictable terrain, sometimes more like piles of rubble than solid rock. A stable near-Earth quasi-satellite like this offers the perfect training ground for future asteroid explorers. Imagine the first generation of mining robots learning to walk, anchor, and extract material right here. Imagine scientists drilling into primordial rock that predates Earth's formation. Imagine using its water content to produce hydrogen fuel for deep space missions. If space exploration has a future economy, quasi-satellites like 2025 PN7 may become humanity's first stepping stones. Beyond the science and engineering, there's something poetic about this discovery. We've orbited the Sun billions of times since Earth formed. Countless asteroids have passed near us, some for minutes, some for days, but a very small number settle into this quiet, harmonious orbit beside us. It feels almost symbolic, like the universe occasionally leaves us small reminders that we're not traveling alone. There's one more detail that made astronomers pause. The orbit of 2025 PN7 is eerily similar to another quasi-satellite discovered years ago, called Comet. To this day, that object carries a fascinating hypothesis. It might be a fragment of the Moon, thrown into space long ago by an impact and captured into a quasi-satellite orbit. Could 2025 PN7 also be a fragment from the Moon, or even from Earth itself? Nobody knows yet. Its reflectivity doesn't quite match typical lunar material, so it looks more like a regular asteroid. Still, the question hangs there, tempting scientists with the possibility that a piece of Earth's past might be orbiting quietly beside us. In the context of 2025's discoveries, 2025 PN7 might seem small compared to black holes, exoplanets, or early universe galaxies, but its significance is more personal. It brings the frontier of exploration right into our cosmic backyard. It reminds us that space isn't just distant stars and ancient galaxies. It's here close, quiet, familiar, moving with us in ways we never imagined. When you look up at the night sky, you won't see 2025 PN7. It's too faint, too small, too subtle, but it's there, tracing a slow, delicate circle around the Sun that always keeps it near Earth, like a companion walking beside us on a long journey. One day, a spacecraft will visit it. One day, humans might mine it. One day, the story of 2025 PN7 might become part of the story of Earth's expansion into space. For now, its discovery is enough. It's a reminder that even after all this time, our solar system still has secrets. Thanks for watching. Here's the thing about 2025. When you pull back and look at the year as a whole, the discoveries start feeling less like separate stories and more like pieces of one larger message coming from the universe itself. A message that says, you don't know as much as you think you do. A message that reminds us that the cosmos is still wild, still unpredictable, still capable of overturning assumptions that felt solid just a year before. By December 2025, astronomers, planetary scientists, and cosmologists were all realizing the same truth. This wasn't a normal year. This was a turning point, because when you line up the major discoveries of 2025, a pattern appears. Not a scientific pattern, but a philosophical one. A shift in how we understand our place in the universe. Let's walk through it, not as a list of facts, but as a story. It starts with a visitor, a messenger from another star system, Comet 3I Atlas. A frozen fragment older than Earth, older than the Sun, older than every ocean and mountain on our planet, drifting alone for billions of years until it wandered into our sky. It came close enough for us to study it in detail. We saw its chemical signature, its surface, its historic scars, and suddenly The idea of interstellar objects wasn't rare or mythical anymore. It felt normal, expected, predictable enough that astronomers started proposing emergency spacecraft that could launch within weeks to chase the next visitor. Then came the discovery of a hidden supermassive black hole in the Large Magellanic Cloud, not blazing brightly, not eating stars, not revealing itself through jets or radiation, silent, invisible. This was a reminder that the universe isn't just filled with things we can see, it's filled with things that refuse to be seen. Then came discoveries from the early universe. The Webb telescope revealed galaxies and black holes that were too mature, too massive, too organized for their age. The cosmic timeline didn't seem to add up anymore. Galaxies shouldn't have spiral arms when the universe was just 10% of its current age. Black holes shouldn't reach supermassive size so early, but they did, and they're out there in numbers. Attention then shifted closer to home. A 10-kilometer moon was found quietly orbiting Uranus, S 2025 U1, unnoticed for decades, and only revealed when Webb blocked the planet's glare. A subtle reminder that we don't even know how many moons are in our own solar system. Then came the Perseverance rover's surprise, a rock from Jezero crater named Chava Falls, whose chemistry and mineral patterns resisted every non-biological explanation scientists offered. Not proof of life, not a smoking gun. You missed something. As if 2025 had decided to push astronomy to its limits. The Lucy mission revealed unexpected structures inside asteroid Donald Johanson. Betelgeuse turned out to be a binary star after centuries of assumptions that it was alone. A new quasi-satellite, 2025 PN7, was found quietly pacing Earth for 60 years, unnoticed. Saturn was found to have 128 new moons, hiding in faint orbits. And then, like a final plot twist, we learned that our entire solar system was moving through space 3 times faster than expected. Each discovery alone was remarkable, but together, they formed something else. A reminder that the universe is alive with motion, complexity, and hidden structure far beyond our neat human models. Here's what ties all these discoveries together. Not physics, not math, not telescopes, curiosity. Human beings looked at interstellar dust, distant galaxies, and faint background radiation and said, "I wonder if there's something more there." And every time they asked, the universe answered, "Yes, keep going." Because for all our equations, simulations, theories, and diagrams, the truth is simple. We are still beginners. We are still standing at the edge of an ocean, holding a small cup, trying to understand its depth by tasting a few drops. 2025 showed us how much we've learned, but also how much we still don't know. For example, consider how small our cosmic neighborhood is. Just 18 light-years away, a small world, GJ 251c, waits in the habitable zone of a quiet red dwarf. Maybe silent, maybe barren, maybe alive. 18 light-years. A cosmic walk, not a cosmic gulf. And as scientists debated that world, another group of astronomers debated something much stranger. Why do our simulations of the universe predict galaxies that don't match what Webb is showing us? Why do our equations insist that early galaxies should be chaotic, when instead they are structured and mature? Some theories began to crack, others stretched themselves to accommodate the new data. A few were abandoned entirely. And every abandoned theory is a sign of growth, a sign that science is willing to evolve. But the biggest shift of 2025 wasn't about any one discovery. It was about how those discoveries changed our perspective. Suddenly, Earth doesn't feel like an isolated world anymore. We exist in a universe that matured faster than our equations predicted. And we are traveling through that universe at nearly 1,000 kilometers per second, a velocity that challenges the very model of cosmic expansion. It's humbling, it's thrilling, and it's a reminder that every time we think we've reached the peak of understanding, a new mountain appears behind it. 2025 wasn't a year of answers. It was a year of better questions. Questions like, what other interstellar objects have passed through our solar system without us noticing? How many silent black holes surround us? Did life once exist on Mars, or does it still exist underground? Why did the early universe organize itself so quickly? Are there forces or structures beyond our observable horizon influencing our motion? And if our speed is 3 times higher than expected, what does that say about the shape and behavior of the universe? These questions aren't small. They are the next frontier of astronomy. And the universe isn't slowing down. The data keeps coming. The telescopes keep improving. The questions keep deepening. Soon, missions will launch to the outer planets with instruments capable of mapping moons we haven't discovered yet. Mars samples will return to Earth, samples that may contain the first direct evidence of extraterrestrial biology. New gravitational wave detectors will begin listening for colliding supermassive black holes in the early universe. And 25 wasn't just a year of discovery. When you look at everything we learned about the universe in 2025, one question rises above all the rest quietly, persistently, almost uncomfortably. This question isn't new. It's the heart of the Fermi paradox. But 2025 made the paradox sharper, more urgent, because the discoveries of this year didn't make the universe feel emptier. They made it feel crowded. We found super-Earths in habitable zones, moons hiding organic chemistry, and interstellar comets passing through our system. All these findings point toward a cosmos that is busy, active, dynamic, a place where complexity emerges early and often, and yet, silence. Not a whisper, not a signal. Not a single confirmed trace of intelligent life. So today, we're stepping back from individual discoveries to look at the bigger picture. What does 2025 mean for the search for life? And why haven't we found it yet? Let us start with the near misses, the discoveries that felt like they were circling around the idea of life without quite touching it. Take GJ251c, the nearby super-Earth. It's in the habitable zone. It's rocky. It may hold an atmosphere. Its twilight region, that permanent strip between day and night, could have liquid water. In 2025, the number of potentially habitable exoplanets within 20 light-years of Earth passed 30. That doesn't mean life isn't there. It means our instruments are just starting to reach the required sensitivity. It's like being in a massive, dark room with a tiny flashlight that only illuminates what's directly in front of your face. Then you have the Mars sample controversy, the Chava Falls rock. It wasn't definitive proof of life, but the chemistry inside it matched patterns we normally only see from biological processes on Earth. Now, this is the kind of discovery that demands patience. But what really matters is this: Mars is not a dead world. It's not a dry, empty planet, frozen in silence. Whether life actually emerged or not, the environment was ready for it. Venus may have once been habitable. Europa and Enceladus have vast hidden oceans today. Titan has complex organic chemistry, a pre-life chemical factory. It's almost as if chemistry itself is eager for life to begin. The universe seems hardwired to assemble it. So why don't we see it? Here's one possibility that 2025 pushed to the surface. Maybe life is common, but complexity is rare. Simple life, bacteria, algae, microbial matsemite, spring up wherever water and energy meet. That could be happening all over the galaxy. But intelligent life, civilizations, technology, those might require a chain of events so long, so delicate, so improbable, that even a galaxy full of habitable planets may produce only a handful of advanced species at any given time. And here's the brutal part: civilizations may not last very long. If the average lifespan of a technological species is, say, just a few thousand years, the universe could be filled with life, but nearly empty of long-term communicators. We might have arrived at the party too early, or, far more chillingly, they may have vanished long before we even started looking. Another possibility is far stranger. 2025 forced us to confront the idea that the universe is structured in ways we still don't understand. We discovered that the early universe formed galaxies way too fast. We saw black holes growing too quickly. We learned that our own solar system is moving through the galaxy 3 times faster than our theories predict. These aren't small corrections. They're huge signs that our entire model of the cosmos might be incomplete. We search for radio waves because that's what we know how to do. They could be using gravitational waves, neutrino beams, quantum entanglement, magnetospheric modulation, or something we haven't even imagined yet. In this scenario, the silence doesn't mean absence. It might simply mean we're deaf. The number of stars we've examined for signs of life is microscopic. It's not 1% of the Milky Way. It's not 1/1,000,000th. It's closer to a billion. That's where humanity is right now, scientifically. Even if life is common, we wouldn't know it yet. Some researchers estimate that humanity would need centuries of continuous observation just to get a statistically realistic sample. In other words, it's simply too early to expect results. But beyond all the scientific explanations, 2025 offered something more emotional, more philosophical. It reminded us that we are still children standing under a night sky so vast that our questions echo more than they get answered. When the star Betelgeuse turned out to have a secret companion star, it showed us that the universe still hides things in plain sight. When Saturn suddenly gained 128 new moons, it showed us how much we miss when we just don't look carefully enough. And when a quasi-satellite was found to have been orbiting Earth, unnoticed, for 60 years, it showed us that profound mysteries can sit right beside us without anyone ever noticing. So imagine what hides in the vast, dark spaces between the stars. And that brings us to the final thought, not a conclusion, but an invitation. Maybe the silence of the universe isn't an absence. Maybe it's a pause before the next great discovery. Maybe life is out there, waiting for us to build instruments powerful enough, clever enough, and sensitive enough to finally hear its faintest whisper. And when that whisper comes, whether it's from a nearby super-Earth, a Martian rock, a hidden ocean on a distant moon, or the atmosphere of a faraway exoplanet, it will redefine everything. Our identity, our religions, our history, our philosophy, our science, our purpose. This is why 2025 mattered. Not because it answered the question, are we alone? But because it reminded us, more profoundly than ever, to keep asking. Thanks for watching. If you found this journey through the cosmos as fascinating as I did, consider subscribing for more deep dives into the universe's greatest mysteries. For decades, the moon felt like a place we used to visit, a dusty museum of old footprints and abandoned flags, a symbol of nostalgia rather than a destination. But 2025 changed that. In that single year, space exploration wasn't just about answering scientific questions anymore. It was about watching humanity take its first real steps toward becoming a multi-planet species, slowly, cautiously, sometimes clumsily, but unmistakably. And nothing captured that shift better than what happened on the moon in January. The United States, Japan, India, South Korea, and several private companies all landed new missions within months of each other. Suddenly, the moon wasn't quiet. It was busy, buzzing, alive with machines. Robots drilled, rovers crawled, and orbiters mapped regions we barely understood. Beneath all that activity was one simple but transformative question. Can humans live on the moon? This is the story of how we began to answer that question. The breakthrough came from a place most people had never even thought about: the shadowed craters of the lunar South Pole. These are regions that never see sunlight, not for a second, not for millions of years. Temperatures there drop below -200 degrees Celsius, making them some of the coldest places in the entire solar system. But they hold something priceless: water ice. We'd suspected it for years, seen hints from orbiters, and detected glimmers of hydrogen. But in 2025, for the first time, a lander drilled into one of these permanently shadowed craters and confirmed it directly. Not frost, not trace molecules, but real, layered, dense, abundant ice. When NASA's VIPER Scout drilling module sent back its results, mission control went silent. Everyone knew what it meant immediately. Water means fuel. Water means air. Water means agriculture. Water means permanent habitats. If the moon has mineable ice, humanity suddenly has a refueling station in space. But that wasn't the only discovery. The Japanese Slim lander, while testing its precision landing capabilities, mapped the rim of Tyoli crater and revealed something strange: a glassy, vitrified crust. This was evidence of ancient volcanic eruptions, far larger than previously recorded. That meant the moon's interior might have remained warm for much longer than we expected. And a warmer interior implies the existence of underground tunnels, lava tubes, and stable caverns, perfect shelters for future bases. Imagine entire research stations built inside ancient volcanic tunnels, protected from radiation, micrometeorites, and extreme temperature swings. Those tubes could be kilometer-long safe zones. SLIM wasn't meant to find that, but like so many discoveries in 2025, the universe had surprises waiting in the dark. Meanwhile, India's Chandrayaan-4 orbiter was detecting unusual hydroxyl concentrations on the highlands near the polar region. This hinted that solar-wind interactions might be producing water molecules continuously. That's huge. It suggests the moon isn't a static, dead place. It might have a slow, ongoing surface chemistry cycle. And if we can understand those cycles, we can work with the moon rather than against it. The lunar environment isn't just something to survive. It's dynamic, predictable, and harnessable. Then came the moment no one expected. A private Japanese company successfully deployed the first autonomous construction swarm on the lunar surface. It was a group of 6 small robots equipped with regolith printers. Their mission was simple: test whether lunar soil could be melted and printed into small, solid bricks. And it worked. They built a 70-centimeter curved wall. It was tiny, yes, but incredibly symbolic, because one day those same methods could build habitats, radiation shields, roads, landing pads, and storage domes, all from local material. In 2025, The moon stopped being just a destination. It became a construction site. But the biggest shock came from South Korea's LunaMap mission. It used deep penetrating radar to scan beneath the Shackleton crater rim, and what they found changed everything. A hollow cavity, nearly 200 meters wide, and possibly part of a larger network. It wasn't just an empty hole. It was a stable subsurface chamber with load-bearing strata, meaning it could potentially support human-built structures. For the first time, scientists saw a place on the moon that wasn't just survivable, it was potentially livable. A natural shelter, a refuge from harsh radiation, a pocket of stability, a place where future explorers might sleep without wearing pressurized suits. But here's the quiet detail most news coverage missed. Every single mission NASA, JAXA, ISRO, carry, the private companies shared their data. It wasn't guarded, restricted, or siloed. It was shared. The moon became the first real test of whether humanity can truly collaborate in space on a large scale. And in 2025, the answer seemed to be a resounding yes. China announced open data for its Change Polar Mapping program. India shared ice distribution models. NASA shared thermal conductivity measurements. Private companies shared their material processing experiments. For once, exploration felt less like a competition and more like a rehearsal for something much, much bigger. There's a moment in every scientific movement where things shift from theoretical to real. In lunar exploration, that moment happened in September 2025 when NASA published its first long-term settlement feasibility report. In calm, technical language, it concluded that a sustained human presence on the moon is achievable by the mid-2030s, provided that water extraction, regolith construction, and nuclear surface power proceed as expected. That's bureaucratic phrasing for something much more profound. We can live there. Not just visit. Live. The moon isn't a dream. It's a destination within our reach. 2025 made